I'm Charles Wilson, Staff Product Cybersecurity Architect at Torque Robotics. This presentation will cover secure design principles. Here's the overall AVCDL training path. If you're taking this training, it's assumed that you've already completed the AVCDL overview training. This training will cover secure design principles. Unlike just about every other aspect of the AVCDL, secure design principles isn't about a specific activity and a specific outcome with specific metrics. It's about a way of looking at how we treat the system and how we approach design from the standpoint of cybersecurity, with an understanding that fundamentally, cybersecurity engineering is about the soundness of the code and the system supporting the code. We're going to look at a set of principles which, when applied, lead to a system which is much more conducive to having the cybersecurity processes and activities called out within the context of the AVCDL applied to that system, and which is fundamentally more secure because it has had these fundamental aspects put in place during its design. As a gentle reminder, we're covering design principles here, not design rules. We're not going to have these completely orthogonal, well-defined, smart-compliant, INCOS-esque rules. What we're going to have is a set of principles, where a principle is a fundamental proposition that serves as a foundation for a system or behavior. The behavior that we wish to ensure is that the system is secure within the context of cybersecurity. The principles are going to be presented in a relatively hierarchical fashion. The ones that come first are built upon by the ones that come later. The list that we have is modularize, minimize surface area, isolate security, isolate privilege, use lease privilege, use hierarchical trust, limit lifetimes, use standards-based cryptography, use adaptive cryptography, use trusted communications channels, enable auditing, and degrade as necessary. Now let's look at each of these in detail. The first principle is perhaps the most obvious and the most overlooked, and that would be to modularize. It's well appreciated that a monolithic design is intrinsically difficult to analyze, build, debug, test, and also, by extension, defend. This is especially true in a cybersecurity context. And so, when we talk about modularization, it's nothing new. Let's look at modularization within the context of cybersecurity. Instead of just looking at function as the basis for modularization, we'll consider things like trust, privilege, and policy. Let's look at some areas where we consider modularization traditionally and how they translate. Let's start with our first area of modularization, and that's refactoring. Here we have a function f, and during our development we decide that there's this useful piece. We decide that we could use it in our other function over here, g. So we simply copy and paste that useful block into function g. Over time, this isn't really a great approach because if the block in question is of a sufficient level of complexity, changes to it in the future become problematic to manage. So what we typically do is switch to an extraction approach and make it its own function and call it that way. The same thing is true for cybersecurity. Cybersecurity, especially in the realm of cryptography, tends to be one of those things that people look at the same way that they look at opening files. I'm going to open a file now, I'm going to do stuff with the file, and eventually I'll close the file. For convenience sake, let's just open it at the beginning of the function and close it at the end of the function. Or worse, at the beginning of the process, we'll acquire our cryptographic bits, put them into the global state, and then we won't have to worry about them. We'll just pick at them as we go. Now, neither the file example nor the cryptographic one are modular in any sense. What you have is this shared state, which is hard to manage, and something that you really could stand to extract, if simply for purposes of being able to test it. At a larger scale, this is all about decomposition. Our system should not just be this amorphous blob that we can only reason on in the context of cybersecurity by using things like penetration testing, which is simply blind QA. It may be perfectly attuned to a non-decomposed system, but that doesn't help us from a design standpoint. What we want is a decomposed system that helps us in the context of cybersecurity. That means that we're going to look at things like the operating system broken down into its processes, things like the file system, process manager, and network manager. We're going to think about resources that we're trying to utilize. Resources may be hardware, so direct hardware manipulation, or they may be data. Do we have third-party components in use? Here we're talking about things like data and audit log managers. And finally, we're going to look at components that we're bringing along to the party. These are our processes, services, and drivers. Our next principle is to minimize the surface area. By surface area, we're talking not about just the physicality of the system, but also the constructs that are within it. So let's look at that. Here's a simple system that's used within the AVCDL to examine various concepts. In the context of surface area, we're thinking about three different things. One is the ports that we have. These are the physical holes in the box. The next are the protocols that run over the communications that traverse the holes in the box. And finally, are the processes that handle the data that's typically traversing the communications protocols and the holes in the box. There are some interesting things to tease out with this diagram. As you can see, the system here is neatly decomposed. On the left is the element that we're concerned with. On the right is the system that's interacting with it. So we have, from this diagram, a good starting point for discussions. The fact that we've chosen ports, protocols, and processes is not arbitrary. These are things that we can look at and we can reason on in a very straightforward manner. They're a very light touch. Essentially, what we're talking about are control points that allow us access to the system. What we're trying to do is keep them to an absolute minimum, because there's no point in having more gates into your castle than you can guard. I'm not going to go into any more depth on this particular point because it's specifically addressed in detail in the attack surface analysis material that we have in both document form and training video form. Our next principle combines the concepts of modularization and surface area minimization. So we'll now address an application of these in the form of isolation of security. Security isolation is going to come in two flavors. The first of which is data security isolation. When we start out with things, we tend to have this structure where we have code and we have our credentials, our cryptographic keys, embedded within the code itself. Our first step in isolation is to take these and move them into a separate file accessed from the code. Better, but not great. What if we have to change them? What if there's a different process that needs to access them? For a third stage, what we have is the code talking to a credentials manager, which deals with the credentials. Here we're showing them as a database. Likewise, as an extension of our modularization discussion, we have communications code that's embedded in the main code. This again is treating our secure communications as sort of a file system. Open it, play with it, and stuff goes on. Our next approach is to take that and again split it into its own file. Our final extension to this is to take that communications code and make a communications manager out of it, which pairs nicely with our handling of secure data. Now let's consider a peer to isolating security, and that's isolating privilege. So we'll start with our simplest case. We have a process, and it's accessing a resource directly. If it's the only process accessing this resource, then there's really no problem. It needs to access it, it can do so, and so we don't worry about it. But we typically don't have situations this trivial. In a more sophisticated scenario, we have multiple threads running within the process. And as we can see here, both threads are accessing our resource. Since the process has the privilege to access the resource, any thread within that process will also have the privilege to access the resource. Ignoring the fact that we now have a situation where there's the risk of a race condition at some point in the future, we have the problem where we now question whether or not privilege is isolated. If we have multiple threads accessing the same resource, we should be asking ourselves, do all threads need to access the resource? And how will we keep arbitrary threads within our process from being able to access that resource? One way to address this situation is ironically by introducing another thread. We give this thread direct control over the resource. This doesn't keep the other threads from accessing the resource, but it makes it less likely that it will happen because we can take certain steps to access that resource exclusively from the thread. We still haven't gotten rid of the problem that we're trying to address, however, which is how do we isolate the privilege? We're basically just isolating the security. The privilege is still associated with every thread in the process. In order to completely isolate privilege, we need to move control of the resource into its own process. This approach meshes well with the isolate security aspect. It also goes along with a recommendation that a resource should be controlled by a single process. This greatly simplifies control and makes it much simpler to test and to mock the resource. And it deals with the case where multiple processes need to access the resource. This brings us to our next principle, that being use least privilege. Extending the concepts of isolated security and isolated privilege. With least privilege, we're going to take a situation like this. We have a process accessing multiple resources. We don't know compositionally what's happening inside the process, but we're doing these discrete resource manipulation activities. In the generic case, these resources require different sets of privilege. And so to have a single process which has 3 sets of privilege is not ideal. There have been a lot of security issues that have come up over the years because a process has too much privilege. These type of constructs are leveraged to do things they otherwise shouldn't. To address this, we echo our previous guidance and employ complete mediation of each resource by adding a dedicated resource manager. This limits the privileges required to the context of each resource manager. If you have a process that needs access to a resource, it should be going through the process which is the resource's owner. If you have a process which doesn't need to manipulate a resource, then the question becomes, is it necessary to access that resource at all? With our next principle, we're going to shift gears a little bit and talk about trust, specifically hierarchical trust. Let's get into what trust is and how it becomes hierarchical. Now let's consider some common entities. For the operating system, there are 3 main entities we care about: the file system, process manager, and network manager. There are others, but fundamentally, these are the ones we work with the most often. On the user side, we talk about processes, so standalone things, services, highly structured and contextualized processes that work within a service manager, and drivers, dedicated elements that do the work of connecting real-world bits to the operating system such that they can provide those bits to the services and processes. So we have these trust levels, and we've established some interesting entities. Let's consider what we mean by hierarchical trust. If we take the simple case where we have process A that wants to communicate with process B, process A uses a communications provider, and that communications provider is a third-party component. So what does it mean for us? We know that the communications provider is something we need to pay attention to, but we also know that it will be talking to the network manager, and the network manager is a trusted component. Additionally, the network driver is also provided by the operating system, so that's trusted. What we're doing here is building up confidence in how we undertake our operations. Keep in mind that this approach can be applied to any set of operations. Now let's look at a more elaborate example. Going back to the example system that we talked about earlier when we were considering surface area minimization, here's its fully expressed data flow diagram, color-coded with trust levels. As you can see, it's not purely hierarchical in terms of trust. We don't go from the operating system through our own code, through the third-party components, to the outside world. We have a partially ordered hierarchy, but fundamentally, we've established the system in such a way that aids us when we're thinking about where to put cybersecurity controls. If we look at something like the core service talking through the web server and eventually to the web browser, we see that there is mediation being done by the operating system components, and those we do trust. Also, since the web server is a third-party component, we'll need to pay greater attention to it. When it comes to external entities, we don't give them any trust. Everything external requires far more control from a cybersecurity standpoint. Overall, what we're attempting to establish when considering trust within the system is what entities we're dealing with. That information will feed into downstream cybersecurity processes. Our next design principle is that of lifetime limitation. Let's consider a relatable scenario. We have a process, we have a resource. We're going to consider the pressure that puts on the system, and we're going to do it over a period of time. At some point, our process starts, and that creates a certain amount of pressure on the system. A bit later, we open our resource, which has an incremental impact on the system pressure. We go along in time, and at some point, we close that resource, lowering the system pressure. Finally, at some later point, we stop the process, which drops the system pressure back down. If we have a finite resource, that being the capabilities of the system, and we exert a particular pressure on it, at a certain point, it reaches its limit and can no longer function in the way that we'd like. So we limit the individual impact of each of our processes and the usage of various resources. You'll notice that the highest pressure exists within the window between when the resource is open and when the resource is closed. Everyone can relate to this example. If we think about it from a cybersecurity perspective, the process is the same. The resource might be a credential we're working with and is therefore out in the open. We're doing this over a particular period rather than thinking about system pressure. In the context of an attack surface, this represents a window of opportunity during which an attacker could possibly gain access to the resource. By limiting the lifetime, we reduce that window of opportunity. That's what we're thinking about from a cybersecurity perspective. Turning it around, the less time that you're using a resource, the less pressure it exerts. The less time that you're using the resource, the fewer variables are in play. Therefore, it makes it easier to debug. Limiting lifetimes has advantages beyond simply the amount of pressure it's putting on the system or the window of opportunity that it's providing for attack. Our next principle is to use standards-based cryptography. Regardless of how much math you studied in school or how many open source projects you've worked on, there's no reason in this day and age to create your own set of cryptographic methods. The number of times that bad cryptography has come out of well-intentioned individuals is well documented. And it's great to say use standards-based cryptography, but which standard do you use when there are so many to choose from? This is a domain-specific issue. It may also be constrained by your supply chain. The best way to handle these cases is to consult with your product cybersecurity SME because they'll be up to date on what the appropriate algorithms, use cases, and key strengths are going to be for the specific domain and use case in question. Unfortunately, it's not enough just to use standards-based cryptography. Our next principle is that we should use adaptive cryptography. As time progresses, even the best cryptographic suite will become susceptible to compromise as computing power increases. This means that the elements of cryptography, that is, the cryptographic function, its use case, and its key strength, all need to be changed over time in order to maintain the same level of security. So let's consider what this entails. When NIST talks about the adaptive cryptographic approach, they use the term cryptoagility. This they describe as the capabilities needed to replace and adapt cryptographic algorithms without interrupting the flow of a running system in order to achieve resiliency. What kind of things are they talking about? Where could this possibly impact us? NIST provides a list that includes the protocols, applications, software, hardware, and finally infrastructure. When we get to the specifics of what's changing within the context of cryptography, then we have three main variables. First, there's the algorithm. This is the use case. It can be hashing, encryption, authentication, or key exchange. Second, there's the cryptographic primitive. This is the math underlying the operation. These include SHA, TDEA, also known as triple DES, AES, and KMAC. Finally is the key strength. Over time, we need to increase the key size for a given algorithm to have the same strength for the current state of hardware. Now let's consider a real-world example of crypto agility done right. For that, we're going to use the Transport Layer Security, also known as TLS. When TLS is used, one of the first things that happens is a negotiation phase, at which time a list of crypto suites is provided by both parties. Now the thing about a crypto suite is that it includes several use cases, and TLS is an example where we use all of the use cases mentioned earlier. Here's one such crypto suite, and this is its official designator given by the IANA. It starts with TLS, which tells us that this is a crypto suite intended for use with TLS. Our next block is our key exchange that we're going to be using. Here, it's specifying the elliptic curve Diffie-Hellman ephemeral key exchange algorithm. The next thing we have is how we're going to be doing authentication. In this case, we're using the elliptic curve digital signature algorithm. Our next block tells us what encryption we're using. Here we're using AES, the Advanced Encryption Standard. We're using a 128-bit key, and we're using it in Galois counter mode. Finally, we have the hashing algorithm that we're using to ensure integrity. In this case, we're using the secure hashing algorithm 256. These 4 cryptographic algorithms are being used in the context of this protocol. It's important to consider that this is just one entry in a list of crypto suites being presented so that a negotiation can take place between the endpoint. They'll establish the most secure of all the suites in common. Using this approach, TLS is future-proof. You don't need to go in and manually adjust parameters over time. You just look to see what standards are evolving toward and provide support for them, or use libraries that provide support for them intrinsically. Also, as various algorithms and key strengths are deprecated and then disallowed, the software only need be updated to remove these options from the crypto suites supported. This has been done before in the case of hashing using RC4. With all this discussion of trust boundaries and cryptographic algorithms and the like, wouldn't it be nice to have something simplified? Our next principle of use trusted communications channels is one of those abstractions which insulates you from having to deal with these other aspects. If you can assert up front that you have a trusted communications channel, then all the data inside the channel is protected, and that's one fewer thing to have to worry about. So why do we care about trusted channels? Earlier we talked about limited lifetimes, and we did it in the context of the analog to an attack surface where we have a window of opportunity where information is present which we wish to keep secure. If you have communication going between process A and process B, going through a system-mediated inter-process communications mechanism, you're going directly through a trusted component that will only provide that data to the intended destination. However, we don't tend to work point to point. We tend to use shared media. We've got process A and process B, and they're traversing a shared medium. Whether that's Ethernet, CAN, LIN, or some wireless modality isn't relevant. What is relevant is that there can be other entities, in this case process C, sharing that medium. Now, ignoring the issue of contention on a shared medium, we have data that's going across it. Unless we can trust the channel that we're pushing the data through, any information we transmit is susceptible to modification, capture, or interruption. And so what we want to do is establish mechanisms that are going to ensure that none of these can occur. We can do this a whole host of ways. One is that we can just not send the information between the two processes. If you don't have to do something, then don't. It's a combination of lifetime and pressure. Do we need to utilize the medium at all? Are we pushing too much through the medium? And are we ensuring that the data that we're pushing through the medium is transmitted in a secure fashion? When we do have a genuine need to communicate securely, then using secured channels eliminates the need to worry about outside interference. As with standards-based cryptography, you should consult with your product cybersecurity SME to determine what means are available in order to ensure that you have trusted communications channels. Our next principle tends to be an afterthought. It's to enable auditing. Let's talk about what it means to perform auditing in a cybersecurity context. I'm sure everyone's familiar with the concept of data logging, where we collect information about the system as it's running so that we can later go back and extract various features to assist in the debugging and optimization processes. Less considered is that in systems which are safety or operationally critical, that it's important to have a separate logging mechanism that's performing an audit function, capturing specific high-level events that occur in such a way that should an event arise which disturbs the system in a way that prevents it from being able to undertake its mission, that that information is recorded. And more especially, that it's recorded in a form which is not subject to tampering. In the case of vehicles or medical devices or other systems of this nature, we want to be able to extract this information as expeditiously as possible. One reason to have a physically separate audit log is the security constraint of having a log which is immutable. This would preclude using just a data log because of the computational burden of enforcing immutability. Having that data be as small and as isolated as possible also reduces the likelihood that we won't be able to extract it should something physically happen to the storage itself. Additionally, we need to consider that in a highly sophisticated system, there's a large amount of data going into the standard data log. If something goes wrong, there's a high likelihood that the last several messages destined for the log will be lost due to buffering. Whereas an audit log has such a low frequency that it's unlikely that you'll drop messages in a similar fashion. This brings us to our last secure design principle, and that's to degrade as necessary. We talked about system pressure and how it can reach a maximum. We didn't talk about what to do about that. In any system that is safety or operationally critical, you should design in the ability to do less in order to ensure that your primary operational goals are achieved in situations where system pressure reaches its maximum allowable limit. Let's look a bit into that. In order to be able to degrade a system and still have it handle its core functions, you must first decide what is and is not important. Now, one could argue that everything is important. Well, if everything is important, then technically nothing is important. You start by identifying the critical elements. Take your most safety or operationally critical elements and put them into a bucket, and those will be considered inviolate. If you can't perform those, then the system has failed. The next set are important features. These aren't at the same level as the critical features, but are those which keep the system running smoothly. Finally, are convenience features. These are features which, if we can't use them, don't impact the system and its functionality. It might not be as elegant as one might like, but that's not the thing that we're considering here. We're talking about those things that are not necessary to directly accomplish the goal. Next, we take those buckets and ensure that the features that we're talking about in both the important and convenience ones are quantized. The coupling level needs to be sufficiently low so that you can turn off a given feature or jettison it if necessary. Let's consider a real-world example and think about what it means in the context of needing to degrade. If we have a communication stream that's coming into the system, then we can divide it as follows. We have the core operation, which is our critical aspect. We have an event processor, which is a high-level handler of events. We have a communications channel handler, which is looking at specific channels that the data is coming in over. Both of these are in our important bucket. And finally, we have the channel listener, which is sitting on a specific modality. We put that in the convenience bucket. Now, this is not to say that if you can't handle data from this, then that doesn't impact important stuff. It's to say that this is less important than the communications channel handler and the event processor. Now let's talk about why this particular arrangement has been chosen. First, let's talk about abstraction level. The channel listener receives incoming packets where the data is fragmented with no intrinsic meaning to the system itself. These packets are handed off to the communications handler, which will then assemble a sequence of packets to form a cohesive message that is then handed to the event processor. The event processor will then send an appropriate command to the core operation. Each of these steps is increasing in abstraction level. Similarly, when we think about this from the standpoint of execution, at the communications listener, execution time is very rapid. You're dealing with a small amount of data. By the time you get to the core operation, the execution time is very large because we're dealing with an abstract operation that we're attempting to engage in. This relationship is flipped when we're looking at queue size. Queue size for the communication listener tends to be large with respect to the size of the data itself. By the time we get to the core operation, the queue size is much smaller because we can only handle so many events. Similarly, at the communications channel, we're expecting there to be a high tolerance for error, whereas in the core, we're expecting that tolerance to be much lower. The coherence of the request needs to be high enough to ensure that the request can be handled. Because of this, if we end up with a situation where the channel listener is being flooded with noise for whatever reason, whether that's solar flares or bad actors or whatever have you, we can take the active step of stopping our active listening and periodically poll to see if the channel is quieted down. One could argue that you don't want to lose data. The problem is that you're trading off the ability to have the processing deal with the core operation versus having processing being chewed up in the churn between the channel listener and the channel handler, which is trying to assemble this information and then pass it down. And so here we can see an example where degrading is the correct way to approach this. This requires that we build in mechanisms that allow us to recognize that we're being overwhelmed and that we can selectively disable and then re-enable functionality selectively. The mechanism of degrading and recovery is worthy of much discussion, but fundamentally, it must be designed in. It can't be easily retrofitted. That covers the secure design principles. Let's take a step back and consider some of the takeaways. The secure design principles are intended to be comprehensible. There's nothing in them beyond the capabilities of systems and development teams to wrap their heads around, which is why it's presented in this hierarchical fashion. The principles aid the downstream cybersecurity activities. As we know, the further downstream you are, when you need to impose a cybersecurity control, the more costly it is in time and resources. There's a possible regulatory element here that can never be overstated when you're in a safety-critical domain. Finally, it should be appreciated by this point that a layered analysis approach to design should be used. This is not simply from a cybersecurity perspective, but from the functional and adjacent safety perspectives as well. For additional information and to get a more in-depth set of references, the Secure Design Principles secondary document is available in the AVCDL GitHub repository. All AVCDL materials, both in source and distribution forms, are available on our GitHub site as shown here. Because of the size of the repository, it's recommended that you either clone the repository or download a zip archive of it if you're not familiar with using Git. Instructions for downloading a zip archive are linked to on the repository's front page. Videos covering various aspects of the AVCDL are available on our YouTube channel, as shown here. It's important to note that all AVCDL materials, except for the introductory blog posts, are intended for product cybersecurity engineering practitioners. With this training complete, you can proceed to one of the other trainings at this level. These include handling PII, secure deployment, requirements taxonomy, threat prioritization, and traceability. Additionally, you can also proceed to apply secure design. Here are the references to the source material used in the creation of this presentation. They'll also be included in the video description. Additionally, this presentation source material will be provided on the AVCDL GitHub repository.